Can you see my screen okay?
Of course, yeah.
Good. Okay, so as Juana so generously already explained, I'm going to tell you a little bit about a project which I'm involved with, or have been involved with for about a decade now, called the Cherenkov Telescope Array. That may well mean nothing to you at the moment. I hope by the time we finish the talk, you'll have a good idea of what we're trying to do. So I'll start off by introducing the subject through talking about cosmic rays, explaining first what they are, and how we can detect them. Then look at how we hope to improve the techniques we use to study cosmic rays and their sources, and go through some of the technical detail that we're involved in at the moment, and talk about some of the physics we hope to study using the new apparatus we're building before I finish with a short summary. Please, if you want to ask questions, do so as we're going through this. And if there's too much detail in any particular aspect and you don't feel it's worth covering here, then just say so, we can skip on to the next bit of the talk. Okay, so let's first look at what cosmic rays are. So these are charged particles like protons or ions, that could be helium ions or heavier ions, which hit the atmosphere coming from space. And these can have energies that range from being low. These are things that typically come from the sun, and those are around about a giga electron volt, or 10 to the 9 electron volts, all the way up to enormous energies. So what do those energies actually relate to? Well, a giga electron volt, or 10 to the 9 electron volts, is 1.6 times 10 to the minus 10 joules, for those of you who are familiar with that unit, or it's about the energy of a red blood cell moving at a few meters per second. Okay, so I hope that's sort of familiar to you. Many of you are being medics. The high energy end of the cosmic ray spectrum includes particles with energies at up to 3 times 10 to the 20 electron volts. That's the highest energy that's been measured so far, which is 48 joules, okay? And that's about the energy carried by a tennis ball moving at 90 miles per hour. And that's absolutely incredible, because the proton or ion which is carrying that amount of energy is absolutely tiny. So 10 to the minus 15 meters is the kind of diameter we're talking about there. And it's incredible that if such a tiny particle actually hit you and deposited all its energy locally, it would A, be painful, might even knock you over, okay, which is almost unbelievable. So the picture on the right here actually shows the energy spectrum of these cosmic rays, starting from the left at the lowest energies, around about a GeV, and going up to about 10 to the 20 electron volts at the right-hand end. And you can see that the number of particles is very large. This is the number per meter squared, essentially. Very large at the low energy end, but drops and is very, very small at the high energy end. So here, for example, we're looking at 1 particle per meter squared per second. Here, 1 particle per meter squared per year. And the high energy end in which we're particularly interested, here we're looking at 1 particle per square kilometer per year. Okay, so these things, the enormously energetic cosmic rays, are very rare. To give you another point of contact with what we can do on the Earth, this is the beam energy of the largest accelerator that humankind has managed to build, the Large Hadron Collider at CERN. So that's about 10 times 10 to the 15 electron volt beam energy. And this is the equivalent center of mass energy of the collisions at the Large Hadron Collider. So you can see that somehow the universe is capable of producing charged particles, accelerating them to energies which are way beyond anything we can do on Earth. Okay, so the next thing that I want to show you is how we know about these particles, and what we believe could be the possible mechanisms that have allowed them to be accelerated to such enormous energies. I'm afraid the way I've got my screen set up, I can't see the chat. So if anybody does ask a question, could somebody just interrupt me and tell me that there's something we to look at? Okay, so this is the primary piece of apparatus that is currently used to study cosmic rays. It's an international experiment that's been built in Argentina. It was first proposed in 1992, and after a couple of decades of work was completed and has been running since then. It's huge. Its area is over 3,000 kilometers squared, so twice the size of Greater London. And it consists of two types of detectors, primarily. There are 1,650 so-called surface detectors and 4 fluorescence detectors, and we'll look at the design and function of those in a minute. More recently, a similar array called the telescope array has been built in the Northern Hemisphere in Utah in the USA. So let's now have a quick look at how the Pierre Auger Observatory functions. Well, in principle, it works as shown in the diagram on the left here. So one of these cosmic rays that we've been talking about comes in, hits the atmosphere, and it interacts with the oxygen and nitrogen nuclei in the atmosphere, producing a shower of particles. These cause the nitrogen and oxygen atoms in the atmosphere to fluoresce. So electrons surrounding the nuclei of these atoms are raised to higher energy levels and then fall back again, raised to higher energy levels by the interactions with the incoming cosmic ray, fall back to their normal energy levels, and in doing so, they emit photons, light. So that's the first thing that the observatory uses to identify that a cosmic ray has come into the atmosphere. This fluorescence light is detected by the so-called fly's eye detectors. Then these particles that are produced in the shower, some of those reach the ground, and on the ground, some of those pass through the so-called surface detectors, these things that are labeled as Cherenkov tanks here on the ground. We'll talk about those in a second. So that's what happens in principle. This is what the thing looks like in practice. Here's one of the houses containing the fluorescence detectors. Here's one of the surface Cherenkov tanks. And you can see this is on a piece of fairly flat ground in Argentina. You can see also that it's solar powered. And this thing here is actually a microwave mast. So to save the builders having to stretch cables from all these detectors to some central location, they pass their information to the central analysis station using microwave. So essentially a bit like a mobile phone system. You can also see in the top right here that Argentina is justifiably very proud of the fact that it was selected as the site to build this large array. And this is an Argentinian stamp that shows one of the surface detectors and the fluorescence detector house here that was in circulation in Argentina for something like 10 years. Okay, so onto the surface detectors, because these are interesting because they're relevant to what we talk about later on as well. So some of the particles generated in the showers by cosmic rays will pass through these surface detectors. And they are a box containing very, very clean water. As the cosmic rays pass through there, they actually travel faster than the speed of light in water. Now, at this point, somebody should shout at me and they should say, well, hang on a second, that's impossible. Nothing can go faster than the speed of light. And of course, you're quite right. Nothing can go faster than the speed of light in vacuum. But when light enters water or glass, it slows down. How much it slows down is given by a number called the refractive index, which is about 1.5 for water. So water, light is traveling significantly slower in water than it does in vacuum. But the cosmic ray particles, they don't slow down when they enter the water. So even if they're doing, say, 0.999 times the speed of light when they're passing through the air, when they hit the water, they keep on doing that speed, and therefore they're going faster than light does in water. And in that circumstance, the particle emits what's called Cherenkov light, which I've tried to illustrate with these blue rays here. And that light is detected by these light-sensitive detectors at the top of the tank after it's bounced around a little bit. And so you know, by detecting that light, that a cosmic ray has passed through the tank. So that's how the surface detectors work. The angle that the light is emitted from the cosmic ray track is something like 40 degrees in the case of water, and that's given by how much the light is actually slowed down as it enters water. You've probably seen Cherenkov light before, perhaps without knowing about it, because if you see a film in which there's a nuclear reactor, for example, then you'll typically see the reactor bathed in water and a blue glow surrounding the reactor. And that is the Cherenkov light. So what's happening here is that radioactive particles are being emitted from the decays in the nuclear reactor. They're passing into the water, which cools the reactor. And because they're traveling faster than the speed of light in water, they're emitting Cherenkov light, and that light is typically blue, and that's what you can see. So this isn't a case of a film director thinking it would look nice in a sci-fi film. It's actually what Cherenkov light looks like. Okay, so the fluorescence light that's produced in the atmosphere is detected using a telescope. So here's how it functions in principle. The light comes in through a window, which protects the telescope from the atmosphere, hits a mirror, which bounces it back onto a detector, and so you can measure that fluorescence light like that. So the detection of cosmic rays at Organe is dependent on both those systems. So in terms of a computer simulation, what happens is a particle comes into the atmosphere, interacts, producing lots of particles, this shower of particles we see here. They decay, many of them not getting through more than the first few kilometers of the atmosphere, but the longer-lived particles, typically muons, are the ones that reach the Earth. So all these things produce fluorescence light because they excite the nitrogen and oxygen atoms in the air. These things actually reach the surface and can make signals in the surface detector. So that's what it looks like if you make a computer simulation of a cosmic ray. And this is a picture of an actual measurement. So these dots here are the measurements in the fluorescence detectors. So those telescopes that look at the fluorescence light produced in the atmosphere. And when the particles reach the ground, they produce signals in the surface detectors, which are indicated by these red blobs here. So by totting up the amount of light in the fluorescence detectors and the signal produced in the surface detectors, you can actually work out the energy of the incoming cosmic ray, and you can also track its position back to where it came from on the sky. So that's how these measurements were made. So we've said that cosmic rays can produce absolutely astonishing energies. How could that possibly happen? Well, we think the basic idea is that the acceleration happens through what's called the Fermi mechanism. So we think that in various environments in the universe, there are clouds of ions and electrons, so-called plasma, being around, and within these plasmas, because the ions moving in the plasma generate an electric current, which makes a magnetic field, you'll have a magnetic field. And if you have a situation where a particle enters, moves in towards one of these magnetic field carrying plasmas, it'll bounce off it because the charge of the particle interacts with a magnetic field and produces a force. It could then hit another cloud containing its magnetic field, bounce off that, move back to the first one, and so on and so on. And if those two clouds of plasma with their magnetic fields are moving towards each other, then it's a bit like having a ping pong ball that you throw between two table tennis bats. The ball will pick up speed as the two bats swash together, and eventually it'll fly off away from the two bats with a lot more energy than it initially had when you threw it between them. So that's what we think may be happening when we talk about, the acceleration of particles produce cosmic rays in the cosmos. Where could this be occurring? Well, you've got to have these clouds of plasma, and they've got to be moving around, they've got to be turbulent. And the kind of place that can happen is around supernovae, around exploding stars, or around active galactic nuclei. So these are galaxies which have a supermassive black hole in the center. As material falls into that black hole, some of it can get expelled along the direction of the magnetic field produced by the black hole, and you get what's called a jet containing lots and lots of ions and electrons. So exactly the plasma that we need to accelerate cosmic rays. Here's an image of a jet. So this is an active galactic nucleus here. It's actually the galaxy labeled M87. And this is a picture taken by Hubble, which shows the visual image of that galaxy. And then this long structure here, which is the so-called jet. And this is the stuff that's been ejected along the lines of the magnetic field generated by the active galactic nucleus here. And this jet is huge. It's 1,500 parsecs, or nearly 5,000 light years long. And this is where we suspect these clouds of plasma shifting around with high relative speeds, maybe bouncing the particles between them and eventually causing the production of these extremely energetic cosmic rays. So, can we simply associate the cosmic rays we see hitting the Pierre Auger telescope with what we know to be the positions of active galactic nuclei? That would tell us where these cosmic rays are coming from. So, of course, that's been tried. So this picture shows an image of the galaxy, okay, or rather the entire cosmos, in fact, in so-called galactic coordinates. So the galaxy is along this central axis here, and this would be looking towards the center of our galaxy. And the black dots show the positions of all the recorded extremely high energy cosmic rays. So these are all the cosmic rays with energy over 55 times 10 to the 18 electron volts. Also visible are the blue circles, which show the positions of the known active galactic nuclei. And you can see it does look as though some of the cosmic rays, like this one, perhaps, this one, perhaps, this one, no, not, this one, yes. Some of them seem to come from AGNs, others don't. Does that mean that AGNs can't be the source of cosmic rays? Well, no. Because as we've already mentioned, charged particles are influenced by magnetic fields. If a charged particle goes into a magnetic field, then it feels a force, which is what allows them to be accelerated between moving clouds of plasma. We've discussed that. But that also means that if a cosmic ray starts off from some source, like an active galactic nucleus, then as it moves through the galaxy, it'll feel the magnetic fields in the galaxy, and its direction will be changed by them. So that by the time it hits the Earth, hitting Argentina, and we project that direction back to where we think the cosmic ray came from on the sky, it's no longer pointing back to its true source, and so we'll not see it as coming from an active galactic nucleus. So that method is not going to allow us to identify with 100% certainty whether these cosmic rays are being produced by sources like active galactic nuclei or not. What we need to do is to find some way of identifying places where cosmic rays are produced using particles that are not influenced by magnetic fields, so that we can point back to the sources from which they actually came after we've measured them. Fortunately, there are particles, photons, particles of light, which are produced in association with the cosmic rays, which we can measure and which we can use to try and find these sources. So as we've said, cosmic rays can be protons. So the kind of thing that can happen at the source is the proton can interact with some nucleus and produce particles like pi zeros and other stuff. And the pi zeros decay very, very fast within 10 to the minus 16 seconds into 2 photons, these particles labeled gamma here. And what we're going to try and do then is detect these high energy photons and see if they can show us where the cosmic rays are being produced, where these interactions are actually happening. So the first way we can try and do this is to use a satellite outside the Earth's atmosphere. Now, we have to do this because when these gamma rays enter the atmosphere, they interact, so they can't be detected directly on the surface of the Earth. If you want to detect them directly, you have to do it outside the atmosphere, so you have to use a satellite. Fortunately, there is one that's been operating for something like 10 years now called the Fermi satellite, and I've used the first 10 years of the Fermi satellite data, selecting photon energies from about 3 times 10 to the 9 to 300 times 10 to the 9 electron volts to plot the locations of all those photons on this picture here. And you can see that these very high energy photons come from, many of them come from the galaxy in this galactic plane, but you can see there are also blobs outside the galaxy which are sources of high energy photons and are nothing to do with the stars in our galaxy. There are other things that are interesting in this, these so-called Fermi bubbles, which are a relatively recent discovery, which indicate, give us some hints about some of the past activity of the black hole in the center of our galaxy, but maybe we'll leave that for another discussion. Okay, so that's one way of measuring high energy gamma rays. You can see there's a problem with it though. Remember the number of gamma rays or number of cosmic rays we talked about at the very high energies, and the number was tiny. Okay, so we were talking about 1 per square kilometer per year. Of course, a satellite by definition has to be fairly small, otherwise it's just too expensive to launch. So if you're only getting one of these particles with a rate of something like 1 per square kilometer per year, a small satellite like this is going, which is a few meters across, is going to see, well, almost never going to see something which is so seldom. So what we need to be able to do is to build a much, much larger detector to give us a chance of seeing a decent number of these photons. And to do that, we have to work on the ground. So how can we detect these high energy gamma rays on the ground? Well, it's sort of related to what we talked about with the surface detectors in the Pierre Auger experiment. If a primary gamma ray, one of these very high energy photons, comes into the atmosphere, it interacts in the atmosphere with the oxygen and nitrogen nuclei to produce electron-positron pairs, as I've shown here. So here's the incoming photon, the wiggly line, that splits to produce an electron and a anti-electron. They can then further interact, producing another photon here, another electron-positron pair, and so on and so on. And you get a shower of photons, electrons, and positrons in the atmosphere. Now we come back to the Cherenkov trick again. Because these electrons and positrons are traveling faster than the speed of light in air, they emit Cherenkov light. Remember, that's what happened in the surface detectors in the Auger experiment. There, the angle involved was something like 40 degrees. In air, the Cherenkov angle is much smaller because the amount that light slows down when it enters air is much smaller than the amount it slows down when it enters water. So the refractive index of water is something like 1.5. That of air is something like 1.01, dependent on the altitude. So the light slows down only by about 1% when it enters air. Okay, so this shower, this cone rather of Cherenkov light that's produced by the fast particles in the shower has an angle here of only about 1 degree. So if you start at 10 kilometers up, by the time you've hit the ground, you've got a cone of light which has a radius of about 100 meters. So we have to try and measure that cone of light somehow, so we can deduce that this primary gamma ray, this high energy cosmic particle, hit the atmosphere. So what we do is we place telescopes on the ground which are designed to measure this Cherenkov light. The Cherenkov light hits the mirror here and is bounced up onto a camera, okay? And what you see is a light flash that's very, very short. It lasts about 10 nanoseconds, so 10 times 10 to the minus 9 seconds. And you try and detect that with a very, very sensitive camera. And here's examples of the image. So what I've done here is the lights hit this mirror, reflected back onto the camera. Now flip the camera around. So we're looking at the face of the camera, and this is what we'd see on one of those telescopes' cameras. Here are the individual photons hitting the pixels of that camera. Then I've superimposed the image from the second telescope, and you can see that they point back to a place which is indicative of the origin of the incoming gamma ray. And if we tot up the total amount of Cherenkov light measured in these two regions of the image, then we can deduce the energy of the incoming gamma ray. So that's the idea. And now we'll have a little look at how that has developed into a sophisticated detection technique over the years. Now this is interesting because it's actually an area in which the UK has been particularly involved. Oh, sorry. Detection of this Cherenkov light from air showers in the atmosphere was actually made in 1953 in Harwell, I think it was, near Oxford. And the guys involved were called Galbraith and Jelly. And what they did was to use a parabolic mirror, which you can just about see here, which was taken from an old Second World War searchlight. They fastened above it a photomultiplier, this thing here, using a retort stand, and they put the whole thing in a dustbin to try and keep stray light out. So this is not the most sophisticated of experiments. So we know that that thing is 18 inches across because that's how big a dustbin is. And that was the first successful detection of Cherenkov light from air showers. Things developed, and in 1968, the same idea was used, but in a much more sophisticated form in the United States. So this is in Utah, in fact. Sorry, no, Arizona. This, the Whipple telescope. And this is, as I say, finished in 1968. And this looks more like the cartoon I showed you before. We've got lots of mirrors focusing the light, the Cherenkov light, onto a camera up here. And after 2 decades of work, which gives you some idea of how difficult this technique actually is, they were able, in 1989, to publish the first observation of gamma rays from a source in the cosmos, the Crab Nebula, using this method. So that's the basic idea we're pursuing further. Here are the current operating arrays of telescopes using this method to identify incoming very high energy photons from cosmos. This is the Veritas array, which is in Arizona, and actually this is where the Whipple telescope was. This is the Hess Experiment in Namibia, and of course the reason that these places have been chosen for these experiments is that the air is extremely clear. If there were clouds or lots of dust or anything like that in the atmosphere, then the Cherenkov radiation wouldn't reach the ground and we wouldn't be able to measure it. And here's the prettiest of them all. This is MAGIC, which is on La Palma and has 2 telescopes of this form here. Okay, so these are the instruments that have been used to do astronomy at these extremely high energies, looking at these enormously energetic photons over the last decade or so. And let's have a look at some of the things they've seen. So as we mentioned when talking about cosmic rays, one of the possible sources of cosmic rays was supernovae. So can we see any evidence of high energy photons coming from supernovae, which would indicate that our idea may well be true? Let's look at supernova 1006. Now, as its name suggests, this was observed in 1006, and that was being recorded in Chinese manuscripts, for example, but has been seen also in by various other peoples. So, for example, there are American Indian records of this new star appearing in the sky as well. So that's, oh, no, it's no longer 1,011 years ago. It's considerably more than that now. Never mind. Okay. This thing is about 6,000 light years away, and its diameter is about 60 light years. This is what it now looks like if you look at it with an optical telescope. You can just about make out a ring around in the image here, around a central star, or well, around something which exploded to generate this supernova, which must have been somewhere around here. Okay, so that's the optical image. If we now look at this in X-rays, we see the green picture that's here, all right? And if you look in low energy gamma rays, you see this blue. If you look at very high energy gamma rays, using the Hess experiment we've just talked about, then you can see the emission from these regions here. So this, what we think is happening here, is that this is the axis of the supernova. So it was a spinning star generating a magnetic field, and the clouds of plasma ejected in the explosion are constrained to lie along the lines of that magnetic field. So this is where these particles are being accelerated by the moving clouds of plasma and generating the cosmic rays and the very high energy photons that we're detecting in the Hess experiment. So Hess, MAGIC, and Veritas have identified many of these sources. As of yesterday, there were 248 of them. About 170 of them are in the galaxy, and of those 248, about 200 were found using these types of telescopes, these imaging atmospheric Cherenkov telescopes. So if you want to learn more about these things, we have to further improve the instruments. We want to make them more sensitive, which means improving the sensitivity of the camera, but also making the arrays larger so we capture more of the Cherenkov light. We'd also like to improve the energy and angular resolution. So let's look at what that will do for us and how we can actually go about doing it. So if we try and get an order of magnitude improvement in the sensitivity, improve things by a factor of 10, then we'd expect that the galactic plane, rather than looking like this, which is what we see with the Hess telescope would start to look like this. So we'd see a lot more sources. That would give us a lot more information about how the acceleration and how about the physical processes that are going on to generate these high energy photons. We'd also like to locate arrays in the southern and northern hemispheres so we can see both the northern and southern skies. And as I've said, we'd get a lot more sources if we were able to do that. We'd also like to be able to improve the energy resolution, but also the angular resolution. We've argued is that these cosmic rays are being accelerated in shock fronts, so plasma clouds moving around things like supernovae or active galactic nuclei. So we'd like to be able to resolve those shock fronts spatially. Current instruments can't do it. What we see is a shock front that looks like this blur here. If we could improve the resolution by a factor of about 5, then we'd start to be able to see the different parts of the structure of the shock front and perhaps identify where the photons are actually being accelerated, which would help us understand what's going on. Of course, better resolution than that would further improve things, but we're starting to run into the limits of what's physically possible there. So the idea is to construct a new instrument composed of lots of telescopes like those we've seen for Veritas, MAGIC, and Hess, spread over a larger area, and in fact using telescopes of different size to cover the different energy regimes that we're interested in. So the initial concept was to have southern and northern telescopes, sites rather, with differing numbers of telescopes. Here we'd have 4 23-meter telescopes, 4 large telescopes in the southern hemisphere, 25 12-meter telescopes, medium-sized telescopes, and 74-meter telescopes, small-sized telescopes, to cover the highest energy region, and this would be in a site in the southern hemisphere. Now, just quickly, the reason that we need large telescopes to measure the low energies is that the low energy interactions in the atmosphere produce smaller amounts of cosmic of Cherenkov light. And if we want to be able to identify that above the background due to the light coming from stars and so on, then we need to collect a large proportion of those photons to be able to see a significant signal. At the other end of the spectrum, where the energy is very high, the number of Cherenkov photons produced, the amount of Cherenkov light produced by an incoming very high energy particle, is huge. So a small telescope is enough to identify that there has been a photon there, so we can trigger on it and measure it. But you need to be able to cover a very, very large area of the ground, so you can get a significant number of these events. Remember, they're very, very seldom. So you want to make these telescopes small as well to reduce their costs. So the sites chosen for the project were La Palma, which we've seen already for MAGIC, and Paranal in Chile, which is where the European Southern Observatory is located. So far, the progress has been that we've got funding for the numbers of telescopes on the southern and northern sites shown here. So there'll be initially no large telescopes on the southern site. There'll be 14 medium-sized telescopes, and there'll be 37 small-sized telescopes. What we'll do now is look at the performance we expect with this array, which is the one that we've actually managed to get funding for, and how we're progressing with the design of the telescopes and the cameras. So here's the sensitivity that we hope to achieve in terms of the energy of the incoming photons and the number of those per unit area multiplied by the energy squared, so that we don't have a very, very steeply falling spectrum. And you can see that the sensitivity of this device that we're proposing is significantly better than the existing systems. MAGIC, for example, here, Veritas here. This is the new CTA array that we're talking about, northern site, southern site. And also, you can see that the energy resolution of the new system is much better than that of existing systems, and also the angular resolution. So we hope with this new array to be able to significantly improve the measurements that tell us about things like cosmic rays, how active galactic nuclei function, and so on. So we'll have a quick look at the design of 3 of these telescopes, the SST, which is the one which Liverpool, the UK, is involved in, the MST, the medium-sized telescope, and the large-sized telescope. And we'll start off with the large-sized one. Now this, as its name suggests, is huge, 23 meters across, so that's this distance here, and its focal length is 28 meters. That's the distance between the mirror and the camera here. Now, in order to catch transient phenomena that only take a very short time, this device, despite its huge size, has to be able to point to any place on the sky within as short a time as possible. So you need to make it as light as possible. So this thing has been built largely out of carbon fiber. The camera at the end here weighs about 2.2 tons. So moving this thing rapidly is quite a challenge. Here's a picture that I took a few years ago of the construction of the prototype large-size telescope on La Palma at the Roque de los Muchachos Observatory. So this is the MAGIC mirror, and reflected in that mirror, you can see the construction of the large-size telescope going ahead. This is the status. Oh, sorry, no, before we do that, this is me standing on the platform with the MAGIC camera. That's me there taking a picture of myself and some of my colleagues reflected in that mirror. And you can see one of the problems that these Cherenkov telescopes have, because they're so large, they can't be easily installed in buildings. That would make them too expensive as well. So they have to stand outside, which means their mirrors are exposed to the atmosphere. And you can see that, for example, this one here doesn't look too good. And there's 1 or 2 mirrors that have been damaged by rain and ice. So you have to design these things to be as robust as possible. Okay, so here's some more about the Roque de los Muchachos. And here's a picture of that telescope moving to look at a different point on the sky in real time. Okay, so you can point to any place on the sky within about 15 seconds. Now, remembering that this camera is nearly 30 meters above the mirror surface, that means that this thing, the 2-ton camera, is being moved around at a speed of up to about 30 miles per hour, and then stopped, very carefully calculated motion, so that it doesn't oscillate. So you can start taking measurements as soon as you reach the point that you want to be pointing at on the sky. So that's actually a major achievement in terms of mechanical engineering. Here's some first tests of that telescope. You can see here the Cherenkov light generated in the atmosphere by incoming high-energy photons recorded on the camera. These flashes are only about 10 nanoseconds long, okay? And they only contain very small numbers of photons. We're actually really measuring the individual light particles here. This is now looking at a source, the Crab Nebula, and you can see that the things that are coming from the number of photons coming from the Crab Nebula is larger than the background number of photons caused by starlight, and so on and so on. And so you can actually, within the space of a few minutes, you can detect the Crab Nebula in these extremely high energy photons, which illustrates the progress that's been made since the Whipple telescope, where it took us 2 decades to find, to make the first observation of this source. Okay, so here you can actually see the source lighting up, if you like, on the image of using this telescope. Okay, so just a brief aside, we know that there has been an eruption of a volcano on La Palma recently. The MAGIC and CTA telescope prototype are sitting here, and so fortunately they have not been directly impacted by the eruption, despite the fact that that's caused significant disruption on La Palma. So there's a picture of the volcano. So the medium-sized telescope is same basic idea. Here's its camera, here's the structure, and we'll move on to the small-sized telescope, which is the one that we've been working on primarily in Liverpool. So this is very different in style to the previous things we looked at. We can see that it actually has 2 mirrors, one here and here, and the camera sits here. So the light comes down, hits the first primary mirror, reflects off the secondary mirror, and is detected on the camera here. Now, this was, we realized about a decade ago that this would allow us to, at least for small-sized telescopes, to build a cheaper, more cost-effective system than the design we've looked at before. And that's because this camera can be made much more compact than the kind of 2-meter scale things we've been looking at for the large size and medium sized telescopes. This allows us to use a different kind of sensor, a more modern silicon-based photomultiplier, rather than the old vacuum tube devices used in the other camera, and to reduce costs and hopefully to improve the quality of the signals that we produce as well. So here's the telescope that we actually designed in the UK. We unfortunately couldn't get funding for it in England, so some French colleagues managed to get to build it, and this is the prototype near Paris. We tested it near Paris, which of course is not an ideal place to test a telescope which is extremely sensitive and registers individual photons, because as you can see in this picture, the night sky around Paris is of course not dark, but nonetheless we managed to identify interactions using that telescope with our camera. Continued the design and development of this system, so moved to using, as I say, silicon photomultipliers with the architecture shown here, and I'm going to skip through this very quickly, and the basic photo detection unit here. And this has given us a system which has extremely nice qualities. For example, you can identify individual photons here. So this shows what you see if one photon hits the camera, 2, 3, 4, 5, etc. You can actually count the number of light particles hitting the camera. As well as sophisticated electronics, you have to do some more unsophisticated things, like make sure that if it rains on the camera, it doesn't damage it. If it hails on it, it doesn't damage it, etc., etc. So we've done all those tests as well. And what we're now engaged in trying to do is getting the funding to build these telescopes, or rather, now we've got the funding, we need to build these telescopes on the CTA site in Paranal in Chile. So this is where we hope to be. It's near the European Southern Observatory's very large telescope here, and they're currently building another one here called the European Extremely Large Telescope. The names they found for these things aren't the most original, I'm afraid. This is why we're there. It's extremely dry. It hasn't rained for, well, within living memory in the area on which we hope to build our array of telescopes, which has the advantage, of course, the sky is extremely clear. There's a disadvantage that it can be very dusty. And see again why we want to be there in this image of some of this is the VLT, the Very Large Telescope on the European Southern Observatory site, taken with a normal camera, and this is the Milky Way. Okay, so compare that to what you see if you go outside, certainly in Liverpool, and look at the sky, and there's no people within 100 kilometers here, so no stray light. So this is a really stunning view when you go and look out at the night sky. Just as an aside, this place, the VLT, actually has a hotel near it. So there's the VLT up on this hill here, and this is the hotel where the astronomers who are working here actually live. And it's been very carefully designed, so this whole thing emits less light, less stray light than a 50-watt light bulb, and it looks quite sexy as a result. So sexy that Land Rover actually used it for some of their adverts. And also, you may recognize this. This is actually this hotel being blown up, in inverted commas, in a James Bond film. So if anybody knows which film that is, they get a gold star. So how are you feeling? Have you had enough? Because we can go on to look at some of the fundamental physics we can do using CTA if you want to carry on.
Tim, I have a couple of questions, if I may ask. Right. So the first question is actually about, so you're talking about these cosmic particles. So are they actual particles, or are they like photons, which has both particle effects as well as ray electromagnetic effects?
So the cosmic rays are charged particles like protons, or they might be iron nuclei, for example, argon nuclei. Yeah. So stripping off all the electrons, you're left with the positively charged nucleus of the atom. Those could be cosmic rays. The photons we're talking about are light particles. So you can think of light as being either composed of electromagnetic waves or discrete particles, discrete bundles of energy which behave like particles, so-called photons.
But the cosmic particles are actual particles, probably protons.
The ones, well, they're all cosmic in the sense that they come from the cosmos. The ones we call cosmic rays are charged particles. The photons are particles of light, and they have no charge.
Okay, right. So the next question I have is, so I understand a lot of money and energy is being used for this kind of research. What actually are you going to find, or what's the sort of aim of all this effort?
Okay, so what the one thing I've mentioned is trying to understand the astrophysics of how the acceleration happens around active galactic nuclei and supernovae. Okay, so what's actually really happening when these clouds of plasma move around active galactic nuclei or supernovae? Is that really what's producing these very high energy particles or not? That'd be one thing. If we can understand how that happens, that tells us about all sorts of things. For example, one of the big puzzles at the moment in our understanding of how the universe developed from the Big Bang is why galaxies grow to a certain size by attracting in surrounding material because of the gravitational interactions. But why do they stop at that size? Why don't they continue getting bigger and bigger and bigger? And if you do if you do simulations of what you expect the size of galaxies to be, we don't see a cutoff. So there must be something happening that prevents galaxies just swallowing up all the material around them and growing and growing and growing. And we suspect that what may be happening is that the supernovae that happen inside galaxies are ejecting material with such an energy that it's actually forcing away the material that would otherwise be gravitationally attracted into the galaxy and would continue to make it to grow. So it looks as though the kind of thing we're trying to understand here through these acceleration mechanisms and the production of cosmic rays may give us an understanding of why galaxies seem to have an upper limit to their size. As they grow, more stars form, some of those explode, they expel particles with enormous energies, which tend to clear out the regions around the galaxy and prevent more material falling in. So those are some of the kind of astrophysical things that we can try and understand using this apparatus. There are other things, the more fundamental physics kind of topics, which I was going to move on to discuss if people are still strong enough.
Yeah, I'm sure we are, because the next thing you're going to talk about is the favorite thing. I actually ask you to cover. But can I just ask one more question, please?
Yes, certainly, yeah.
So from the little physics I know, there are three possibilities of the expanding universe. It continues to expand forever. It just stopped expansion and then stable. And then the next possibility is the contraction. So now you said something like, oh, it's stopping. So is that now established physics that that's the right thinking of the universe expansion?
Well, it looks at the moment as though what's happening is that the universe started off, we'll start off with the Big Bang. There are things that happened before the Big Bang, which people now are beginning to understand, but we'll not touch on those at the moment because that would take us another few hours. Yeah. So from the Big Bang, the universe expanded, and the expansion slowed, but after a certain amount of time, it started to speed up again. Yeah. So what we now see is that the universe is actually, its expansion is not slowing, but it's accelerating again. So it looks almost certain that the universe will not collapse again or end up stopping. Yeah, it's going to continue to expand indefinitely.
So where does the universe get that additional energy to start expansion again?
Well, the answer to that is it's not known. We can tell you what it must be in the broadest principle. There must be some source of energy, and people, for the sake of having a word to describe it, it's called dark energy. I have to go back then to the phase before the Big Bang to explain a little bit about why we have that idea. So there are very good reasons for believing that before what we originally called the Big Bang, there was a phase in which the universe started off absolutely tiny and then expanded with exponential speed. Before it started the phase which would, going back 10, 15 years, would have been called the Big Bang. Yeah. Reason for believing that is that the universe is much more homogeneous than it should be, because you can't. This is going to be quite hard. Okay, so if you look at a place on the universe to your left on the sky, and then a place to the right, okay, then they shouldn't be the same, because there's no way that light can get from the place on the left to the place on the right in the time that it's had since the universe was born. So there's no way atoms here can tell atoms here what they should look like. And in particular, there's no way atoms here can tell atoms here what temperature they should have. But when we measure the cosmic microwave background, we see that the temperature variations between here and here are absolutely tiny, at the level of 10 to the minus 5, 10 to the minus 6 in terms of a proportion, okay? So the only way that we can think of that could have been the case is that those two areas, two regions, if you go back far enough in time, were actually adjacent to each other, were so close that light could move from one region to the other. So they could be, for example, at the same temperature. They could organize to be at the same temperature. And then an extremely rapid expansion happened, which blew those pieces of the universe so far apart that light can no longer travel from one to the other in that time. Okay, so that's Alan Guth first came up with this idea, and it's the expansion of the universe. This exponential expansion of the universe could describe that and various other puzzles that were not explained by the Big Bang picture. Now, you use that kind of rapid expansion by having a field that contains energy, release that energy to produce the expansion. And we suspect that one possible mechanism for this dark energy is that there is some kind of field like that currently releasing its energy into expansion of the universe. So I'm afraid I'm struggling to put this across in the time I've got here, but there are sort of at least mathematical ways this can be done, some of which give physical predictions in terms of the way the universe looks today, which seem to work pretty well. But we don't know what the actual nature of those fields is. So the one that's called, that produced, so...
No, this guy asks questions. Rowan.
Yeah, so you please ask questions, yeah. So the field, when I say a field, I mean the mathematical description of something like electromagnetism or something like that, okay? And if you have a mathematical description of this system that was able to produce energy to expand the universe, that we label that thing a field. The field that caused that initial inflation is called the inflaton, because it sounds sort of like inflation. And what is driving, and we have hints as to how that must behave to produce the universe as we see it. That we suspect something similar is driving the much more recent expansion of the universe, but we actually paradoxically have less idea about that than we do about the inflaton field in the initial phase of the very, very early expansion of the universe. And when I say early, I mean with the first 10 to the minus 33 seconds. So absolutely tiny lengths of time.
Thank you. Let's give a chance to the other people, and then we'll continue with your presentation again.
Yep.
Can I ask a very simple question?
Yep.
The choice for Argentina, is it the geographical latitude, longitude, or availability of land, or what are the factors which?
It's all sorts of stuff. It's the availability of land. You've got to have, something like Greater London without an awful lot of people on it. It's got to be at an altitude of something like 2,000 meters is about right for this kind of experiment, because that gives you the right depth of atmosphere. If you're going to run systems like fluorescence detectors, you need the atmosphere to be very transparent. So you need it to be a place which is free of lots of dust and so on, and you don't want lots of light pollution from local towns if you can avoid it. The latter, that kind of criterion is particularly important when you start to look at Cherenkov light. As I said, when we're measuring the Cherenkov light, we really are measuring individual photons. So the level of light, over a period of minutes, the amount of light from Cherenkov radiation is absolutely tiny. You couldn't possibly detect it above the normal background light just from stars, let alone if the moon was out. You'd be hopelessly lost. So you need it to be dark. And the only way it works is because for a period of about 10 nanoseconds, the Cherenkov light level for that very, very short time is sufficiently high for you to be able to see it above the level of the standard starlight background. So to do the Cherenkov experiments, you need to go to the darkest places on the planet with the clearest skies, which of course are also the places that are used for optical astronomy, because that's the same criterion as you need for optical astronomy.
Just a very quick follow-up on that. If Argentina was not available for whatever reason, what would have been the second choice?
Well, to be honest, I think the first choice would be places like Chile, in the Atacama Desert, where we're building CTA. We couldn't do the Auger experiment, couldn't be done on the Palma because there isn't the space. Okay, the Palma is difficult for us because it's too mountainous, so it's very difficult to put a large number of telescopes down, and actually just build the things. It's too steep and rocky. So I mean, I think if the Pierre Auger people had their time again and had the resources to build the infrastructure and so on, they'd like to go to Chile as well. But they then have to wrestle with the problems we have. There aren't any roads to take us to where we want to build our telescopes. There's no power there. There's no water there. So first we have to build roads. Then we have to get some power lines in there. And we have to find a way of, bussing in or driving in water every day to mix concrete, etc., etc. So it becomes it's a major civil engineering job, quite apart from the technical difficulties of building telescopes. Yeah.
Thank you.
There are two other questions, but can I point out that this is the burning question time, but a proper question time will be given at the end of the lecture, which will be led by Pavan. So, Mr. and Jihan, if you have a burning question, ask now. If not, we will let Tim continue with the presentation and then ask at the end, whichever you want. Just speak out and let me know, please.
Burning question.
Okay.
Go ahead.
Can I ask it now, if all right? Yeah. So Stephen Hawking had estimated that the Big Bang, for the fine-tuning of the Big Bang, considering critical density, magnetism, and gravity and things like that, is 10 into the power minus 60. Now, 10 into the minus 50 is the cutoff point for normal probability or the chance of happening it normally is 10 into the power minus 50. So how would you explain such fine-tuning of the Big Bang?
Well, this is exactly the kind of thing that I was talking about before. The chance that you have the temperature here and the temperature here, being the same, without any communication between those two regions, is essentially zero. Okay, only if you can have communication between them, if light signals can go from one to the other, can you explain why they might have the same temperature. And that's where this idea of inflation comes in, this very, very, very rapid expansion, which allows you to have essentially, prior to what was labeled the Big Bang, originally, you have a much, a system which is absolutely tiny, and which it's blown up to the Big Bang size, the start of the Big Bang, which is also very, very, very small, of course, but that allows you to have these places that are now separated from each other, that they can't communicate to each other. That allows you to have them close enough to actually influence each other, make sure that the temperature is the same here and here, and stays the same as the expansion happens, this inflation happens. And so you can explain why this bit and this bit are now have the same temperature. So that's sort of the fine tuning that I presume you're referring to, that kind of thing. So that's why this apparently weird sounding idea is actually quite compelling. It's about the only way we have of explaining various properties of the universe, including that similarity of temperature.
Very much.
Okay.
Shihan, can your question wait, or do you want to ask it now?
We'll ask it now. Ask it now.
Yeah, please.
Yeah. Thank you very much, Tim, for this very interesting talk. There are two burning issues that comes to mind. One is, of course, at the beginning of the Big Bang, there was matter and antimatter, and now we know that antimatter is really not there, or we don't see it. The first question is, could it be that antimatter somehow in that very initial phase swallows up a lot of the matter and thereby can become dark matter and dark energy, leaving the remainder, the tiny 4%, which consists of the universe today? So that is a thought I have had, that there could be some kind of initial explosion where the antimatter somehow perhaps eats up a lot of the matter, and then it becomes, so to speak, neutralized and gets into the dark phase. That is one question. And the second one, which you now explained very well, which had puzzled me a lot, was Alan Guth's inflation. As you said, as I understand it, you can imagine it to be a two-phase Big Bang, so to speak. There was a very tiny one, which led to a very exponential inflationary phase, which then came up to a larger size, so to speak, ball. The tiny ball kind of became larger size ball with the temperature of the various points then having been more or less the same. And at that point, the real Big Bang occurred, and as we see it now, so that all the, as you pointed out, I think all the separated points have a very similar temperature, and this can be explained on this particular model. So I wanted you to give some comments.
Okay, so back to the matter-antimatter asymmetry. So that remains a puzzle. It's probable that most of the matter and antimatter, assuming that was generated in equal proportions initially, has annihilated. So but a very, very small proportion of in the annihilations, for some reason, a very, very small proportion of matter tended to exist or to survive matter than antimatter. And that's a very, very small number. I can't remember exactly. I think it's about 10 to the minus 9 is the level of violation needed to create the amount of matter we see as opposed to the antimatter. Okay, the rest has annihilated to produce, we think, primarily photons, so light particles.
Oh, right. Yeah.
And if you do that kind of model, then you can sort of explain the proportion of photons to matter particles that we see in the universe, but we don't understand where this basic asymmetry in the interactions comes from.
Yeah.
If it's tied up with dark energy, and dark matter, I don't think anybody knows.
Yeah,
that remains, that kind of detail we just don't understand. So that's the kind of thing we'd love to be able to sort out.
Right. Okay. Then what about the Guth model, the double, so to speak, what I term the double Big Bang kind of model? The very tiny piece explodes exponentially to come into an intermediate kind of size, and then the real Big Bang occurs. Is there any evidence, or is that the picture that you have at the moment?
That's the picture that is broadly accepted at the moment, yes.
Oh, right.
And when I say broadly accepted, I think, we're talking about 98% of people who think about these things.
All right. Well, thank you.
It really is now, as weird as it may sound, it's the currently accepted theory.
Right. Thank you very much. Tim, let's continue because we'll give another chance for the audience to ask questions later.
Okay. So we've mentioned dark matter a few times. So let's talk a little bit about what that is and why we think there may be dark matter. So the first strong evidence for the existence of dark matter was found by looking at galaxies like that shown here. So this is an image of the pinwheel galaxy, rather, taken by the Hubble telescope. And what you can do is you can look at a star at some point out from the center of the galaxy, and you can watch its motion, and you can work out how fast it's going, and you can look at the distance from the center, and you can work out how much mass there must be within the orbit of that star to ensure that the gravitation between the star and the mass contained in the galaxy is enough to prevent the star flying off out into space. And what's consistently seen is that galaxies shouldn't exist if there isn't mass in the center of the galaxy or mass associated with the galaxy which is not visible. If you just tot up all the mass that's in stars and gas that you can see in X-rays and things within the orbit of that star, then it's not enough to hold the star bound within the galaxy. It should fly off into space. And it's not a small effect. We're short of something like 5 times the amount of mass. Okay, so there must be something there that's producing the gravitational force necessary to hold stars in their orbits. Because we can't see that matter, it's being called dark matter. Right, so that's one piece of indirect evidence for dark matter. There's another, there's actually many things, but some of them are more difficult to see easily than others. So let's have a look at another which is particularly clear. So this is an image of what's called the bullet cluster. And actually, it's 2 clusters of galaxies, one on the left here, one on the right, which have moved through each other. So the one on the left is moving off in this direction, off to the left of the picture. The one on the right is moving off to the right. And they've passed through each other at some point in the past. Now you can see that the way these clusters are illustrated on the picture, they've both got 2 colors associated with them. One's a sort of blue color and the other sort of pinky color. Pink is taken by looking at the X-rays produced from these 2 clusters. X-rays are generated when the atoms in these 2 clusters interact with each other and produce very high energy light. The blue images are identified by using what's called gravitational lensing. So if you look at a very distant galaxy, and I'm going to have to wave my hands here. So here we've got a galaxy, Here's a very distant galaxy, and here's us. Now, the light traveling from this very distant galaxy gets bent by the intervening galaxy, okay, and focused so that we see it coming from not this point here, but either above or below. And typically gives you if you look at something, you can see the distortion of the light coming from sources behind the galaxy, and you can use that distortion to work out how much mass there is in that galaxy. So that so-called, that technique has been used, that gravitational lensing technique has been used to produce an image here, which shows you where the mass in this cluster is concentrated. So the mass here extends through the blue area, the mass here, through the blue area here. The X-rays, which come from normal matter, are here and here. So what you can see has happened is that as these clusters have moved through each other, the normal matter has interacted and slowed down. Majority of the mass, the dark matter, has not interacted and just passed through. So it's tended to separate from the normal matter. So we've got dark matter, normal matter, dark matter here. And this is showing us that we do have normal matter as we expect. We've also got this other stuff, which is carrying mass, but is not interacting in any other way, as far as we can see, apart from through its gravitational force. Okay, so those are two examples of evidence for dark matter. And what we'd now like to do is to understand what dark matter is. There are lots of possibilities. One is that it's so-called weakly interacting massive particles, which, because that's a mouthful, people call WIMPs. So the assumption is that the stuff that's the mass here that's causing this deflection of the light, which we're using to identify where the mass is, where the matter is weakly interacting massive particles. So things with many times the mass of protons, maybe 1,000 times the mass of a proton and upwards, but that only interact either through gravity or perhaps through another weak force. So if that's the case, we might be able to find these particles using CTA if they occasionally annihilate. So one WIMP particle hits another particle, producing photons. Because of the very large mass of these particles, the energy of the photons they would produce will be large. They could travel to the Earth. We could see them with CTA. And what we'd see would be high energy photons coming from regions in the sky in which there is no apparent astrophysical source. Okay, so we'll be looking for high energy photons coming from places in the sky where there is no supernova or no active galactic nucleus. Now that sounds easy, but in fact, if you remember the picture from the Fermi satellite I showed you before, there are lots of background photons that are produced by the interaction of cosmic rays with gas traveling, gas between the stars, intergalactic matter, and you have to disentangle that signal from the signature of WIMPs. Now, how could you do that? Well, you could do that by finding a particular energy of photon produced by WIMP annihilation, because these particles would have a particular mass. When they annihilate, they will produce photons with a particular energy. So instead of seeing all energies with the expected distribution, you might see a spike at a particular energy, which is due to the annihilation of your dark matter particles at that particular mass, their particular mass. Okay, so that's one thing we could try and do with CTA. And if we can find a signature for dark matter, that would help us to understand what's really going on in these processes. That's one possibility for the dark matter. Another is a thing called axions, or axion-like particles. Now these are produced or could be produced in phase changes, interactions in the very early stages of the universe. And instead of being very heavy, like the WIMPs, these would be extremely light. How could we find those? Well, this is a complicated tale. At the moment, what we'd expect is that if you look at a remote source of very, very high energy photons, for example, an active galactic nucleus, and you try and look at those from Earth, what we'd see is that as the photons move from source to us, they're traveling through the universe, and every now and again, one of these photons would hit a photon that's been emitted by a star or is a relic of the Big Bang, and in that interaction would produce an electron-positron pair. So if you look at a remote source from the Earth, then you'd see fewer photons which can interact like this than you'd expect. And that changes the shape of the energy distribution of the source that you measure on the Earth. And from that, we could actually, which would be interesting, we could actually work out the density of the photons in the universe produced by stars and by the cosmic microwave background. So that in itself would be an interesting thing to do. If it would, for example, allow us to learn about how the first stars switched on, okay, how they started producing light. Now, if in addition to the standard physics we understand, there were these axions which were responsible for dark matter, then what happens there is that interactions with the axions, with the magnetic fields in the galaxy, convert photons into axions. Okay, so here's a photon, it has an interaction with the intergalactic magnetic field, turns into an axion. These things are no longer subject to this interaction, so they're not blocked out by the extragalactic background light or the stray photons in the universe. They can travel all the way to our galaxy, where they can convert back to photons in the galactic field, in the magnetic field in our galaxy, and then we'd see them. Okay, so that's an indirect way we could use CTA to try and identify if axions or axion-like particles are what are causing this, are responsible for the dark matter. Okay, so that's another thing we could try and do. Related to that again, is we could try and use this same kind of idea to work out what those intergalactic magnetic fields are. Okay, so again, let's look at a very distant high energy source, and doing as we said, it's interacting with the extragalactic background light or the cosmic microwave background, these stray photons, to produce an electron-positron pair. Now, if there are strong intergalactic magnetic fields, as we've said before, charged particles feel magnetic fields, they feel a force due to magnetic fields, and therefore they radiate more photons. Okay, that's how our showers were being produced in the atmosphere, for example, when they interact in the atmosphere. And so instead of seeing single very high energy photons when we look at a remote source, we'd see some single very high energy photons, but also they'd be surrounded by lower energy photons produced from the electron-positron pairs that can occur, that can be split up by these intergalactic magnetic fields. So if you've got a strong intergalactic magnetic field, when you look at a remote source, you see the heart of the source here. These are the highest energy photons here, but you see a halo of lower energy photons surrounding the source because of this mechanism. And that allows you, and the more halo you see, okay, the bigger the intergalactic magnetic fields must be, because they are needed to bend these E plus and E minus particles further apart. Well, that allows you to measure the strength of the intergalactic magnetic field, and there's almost no other way of doing this. Now, you might say, well, that sounds like a fairly obscure thing to want to do, but this goes back to exactly the kind of questions that people have been asking. How strong the intergalactic magnetic fields are depends very much on the mechanisms around about the Big Bang and the generation of the universe from its earliest times. So understanding these things is important in that context. It also helps because these are the things that get grabbed and concentrated in the formation of galaxies. It also helps us to understand the galactic magnetic fields we see today, which are otherwise, which are a bit of a puzzle. Okay, I think that's probably about all I want. Oh, no. Okay, so just about 2 days ago, an interesting paper came out which pointed out that the intergalactic magnetic fields and how they are, how can influence the formation of the first stars. And varying the intergalactic magnetic field can change the speed with which the first stars switched on by a factor of about 10. So it's not a small difference, it's a very big effect. So what happens is that when the first stars start to form and pull in material gravitationally, that material is often a plasma, charged particles, and if there are magnetic fields around, then the charged particles feel the force due to the magnetic field, and instead of being sucked directly in to the star and rapidly forming a star, they end up being delayed through their interactions with the magnetic field, and the star formation takes a lot longer, and the switching on of the first light after the first starlight after the Big Bang can be then delayed. So even these things that sound esoteric can have a big influence on the structure of the universe as we see it today, and understanding them can help us to understand that structure. Okay, so that was where I was going to stop. What have we seen? We've seen that we are constantly being bombarded by cosmic rays. Some of these have energies which are absolutely astonishing, like a 90-mile-per-hour tennis ball. We've understood that the best way, whoops, sorry, I've just killed that. See if I can get that back.
Right. Tim, can you hear me?
Yeah, I'm just trying to rescue my screen, which
Okay. Nice.
seems to have vanished.
All right.
So what's going on there? Okay, so with a bit of luck, now I should be able to show it you again. Okay, with a bit of luck, that's now visible. So, as I was saying, what we look at is that cosmic rays are continually bombarding the Earth, and that to measure those, we need to measure the very high energy photons they produce. And that these can be studied using telescopes on the ground, which exploit the fact that the incoming photons produce showers of particles and hence Cherenkov radiation. And these give us an insight into some of the most violent events happening in the universe at the moment, and also help us to learn about some of the fundamental physics problems we have, such as what's the nature of dark matter. Okay, so that's everything I wanted to say. Let's have a chat.
Thank you very much, Tim. So this is the question time, and I think I can see Udita already raising his hand up. Udita, please.
What are your thoughts about multiverse?
Okay, so this is another difficult one. The idea here is actually that if you look at this inflation idea, okay, then what you've got is you produce. I'm going to have to be fairly hand-waving it. You produce from essentially nothing this tiny wee seed, which undergoes rapid inflation to produce a Big Bang universe. Now, you can get this from nothing because the energy you've got in your tiny universe is, some of it is positive, but the gravitational energy is negative and balances that out. So you start from nothing, you get a plus and a minus, a +1 and a -1 if you like. So if you were able to put everything back together again, you'd still have nothing. So you're not violating energy conservation. What you're doing though, through this mechanism of the rapid expansion, is you're blowing things apart so that you can't recombine stuff to make nothing. You start off with nothing, you get this wee tiny seed, which then does the inflation, then you've got a Big Bang, which forms a universe. Okay? Now, if you've got something coming from nothing, then you can have lots of things coming from nothing. So there could be many similar systems starting from nothing, producing a seed, which gives the so the quantum fluctuations giving you a seed, which is then inflated to make a Big Bang universe. And you could have lots of them floating all over. You know, there could be an infinite number of those things. The universes would never be able to talk to each other. They'd never see each other because they're all the information, all the light traveling from one to another is all confined. What light traveling around is all confined with each individual universe. So, is this then completely wild and ridiculous speculation? If you go back as little as 5 years, the answer would probably have been yes. But more recently, people have started to think about, are there any statistical things that can tell us whether this idea might have any basis in reality or not? So, what do we mean? Well, if you've got all these different universes being produced, there's no reason why the laws of physics in universe 1 should be the same as in universe 2 or in universe 4736 for that matter. So you could assume perhaps that each universe has its own set of physical laws, and the only place where people would be asking questions about the nature of a universe or the multiverse would be in a particular universe like ours, which is suitable for the development of life. Now, if there were any quantities which were not critical for the development of life, but were statistically associated with quantities, with laws that are necessary for the development of life, and we were to look for those quantities in our universe and find that they were in the right place, that would suggest that the multiverse theory is possible. It wouldn't prove it, but it would suggest that it's a possibility. On the other hand, if any of those critical quantities, or those quantities which are not critical for the production of life, but are associated statistically with conditions that are suitable for life, were found to be way off, that would rule out the possibility that there are multiverses. So this is not yet an area of experimental physics. It used to be an area of wild speculation, but in the last few years, the first hints have started to emerge of how ideas about the multiverse might actually be subject to some sort of experimental investigation. Okay, now that's very vague, but I think it's fair to be vague because I don't think, certainly I don't understand this in depth, and I don't think many people do. So watch this space, I think, is the message. 5 years ago, as I said, we'd have said, rubbish. I would have at least. But now ideas are emerging which start to make experimental investigation of this idea come a bit more realistic, at least.
Tim,
Can I just
just one thing. Tim, can you unshare the screen so that we could see you in the live screen, please?
Yep.
And then Udita can ask a question after that.
Okay, that should have killed that.
Thank you very much. Udita, over to you.
Right. Sorry, you brought up about life. Just want to ask a question on those terms. Milky Way has got about 400 billion stars, and I believe there are about 200 to 400 billion galaxies in the universe. I hope I got the numbers right. But with regards to life, do you feel that we are unique?
I personally would be surprised. And I think that might be, well, part of my reasoning is that I suspect we don't understand the formation of life very well in terms of the fundamental physics. So if you try and think about, the likelihood that something like DNA forms through some sort of random process, it's tiny, yeah. So I suspect there are areas of non-equilibrium thermodynamics which make the production of life, once a certain basic set of criteria are established, much more likely than naive calculation would tend to suggest. Now I can't tell you anything serious about that, because non-equilibrium thermodynamics is a very, very difficult subject. It's not my area of expertise, and it's not the case that anybody is able to do serious calculations that back up my feeling. But I think that the chance of life emerging without something which we haven't understood properly in terms of the physics, this non-equilibrium thermodynamics is so small, even on the Earth, that the fact it has happened means there is something out there, something happening which we don't fully understand, which will also play a role in many other places in the universe. So I think the chances that we're alone are very, very small.
Thanks.
Thank you very much. Any other questions?
Rohan, can I ask a question, please?
Please go ahead.
Tim, thank you very much. The more I listen to people like you, the more I realize that I will never understand anything properly. I don't think it's possible for human beings to understand it properly.
I think that's a condemnation of my ability as a teacher, I'm afraid.
Not really. What interests me is, for me, I suppose the most important thing for me as a human being is the happiness of myself, my fellow creatures, communities around the world. And if science helps to dispel myths or create something new which helps people, for example, electricity has been a great boon, transport has been a great boon, the discovery that illnesses are caused by, a lot of them are caused by bacteria and viruses and not through some kind of divine intervention, has helped humanity. So as far as the research that you have mentioned, what have been the direct effects on human society to make it better? How has it contributed to make human lives better at this moment in time? I know you can't predict the future, but so far, we all have scientific curiosity, and that is essential, of course, for human development. But as you see it, what are the things that in your sphere which has made human life better societies, better communities?
Okay, so well, I think it depends what you mean by direct. Whether dark matter exists or not will probably have very little immediate influence on the quality of human life. Yep. But what does have an influence, I think, are the discoveries that are made, the developments that are made in trying to understand these scientific kind of questions. So I've been talking about the camera that we've been developing, okay, and I showed you the ability of that camera to measure individual photons and to record their times of arrival with precisions of about 100 picoseconds. That's 0.1 nanoseconds. So one of the things you could do with the kind of sensors and electronics that we've developed would be to use those systems in PET scanners. One of the backgrounds in PET scanners is just the random association of a photon here with a photon here, which you assume comes from a decay in your patient here. And if you get that wrong, you get the position of the decay wrong. So if you have a background photon combined with a real photon here, and you connect them up, your assumption is, or your calculation ends up with you thinking that the tumor in which that photon pair was produced is in the wrong location. Now, if you tighten up the time resolution of the PET scanner using the kind of sensors I've talked about, you can reduce the errors involved in that scanning process. Further, the silicon photomultipliers that we're using, rather than the conventional photomultipliers that were in use in PET scanners until relatively recently, or scintillation detectors, can be used in magnetic fields. So it makes combined function MRI and PET much easier. That's the kind of thing where I think astronomy, high energy physics, and so on have driven technologies which have the potential to improve human life. Yeah. as far as I can see, the two major drivers of that kind of development have been science and war. Okay, so the other place, unfortunately, where human ingenuity is driven at a pace and with a resource level which is otherwise not available, is if countries go to war. And my personal preference is that we do more science and a bit less war. Yeah.
Thank you very much. I very much endorse what you say. Certainly, if you look at things like climate change, without science, I don't think we'd ever understood the implication of climate change. So I'm very keen on, but I know that personally, I will never truly understand the sort of things that you understand, and I don't think I ever will. But that doesn't matter. If the outcome of what you find has consequences which are beneficial, that's what matters to me.
Yep, no, I agree. I think this is one of the major messages we have to get across as scientists, that what we're doing is not, some people assume it's somehow rather mechanical and doesn't require creativity in the same sense that writing a novel does or something like that. And I think that puts some people off science. Yeah. So I think we have to try and get that message across, that doing science is actually a really challenging intellectual activity, which is exciting and as fundamental to human culture as is music or something like that. Okay, that's one thing we should get across. The other is that it really can produce, directly or indirectly, significant benefits for humankind. Of course, it can also produce enormous problems. You could argue that it's through the science of steam engines, etc., that we've ended up with a climate crisis, because that's what's produced the CO2. Now, of course, if we hadn't had those steam engines, etc., we'd probably still be living in caves. But you can understand that there are two sides to this. The scientific technological advances we make can have negative effects as well as positive, and it's our job to try and make sure that we do the best we possibly can to ensure that the positives outweigh the negatives and to mitigate the damage that's been caused by previous technological advances.
Thank you very much.
Okay, Sam, your chance.
Thank you, Tim. It's fascinating and quite advanced. Me being a retired gynecologist, I did gynecology for last 50 years, but nothing else. So my friends asking me to come out of that tiny hole of a human female. I'm trying hard. My question is, following from Udita, in religious belief, they talk about 31 levels of existence. Is there some scientific correlation on where the rays come from, cosmos or galaxies and things? Is the number 31 comes into the science?
Not that I'm aware of. No. I'm very wary of these things as well. There's a coincidence. The number of seconds in a year is pi times 10 to the 7. So it's 3.14 times 10 to the 7 seconds. Now, sometimes as a rather nasty trick, I ask my students to explain why that's the case. And it's pure coincidence. Yeah. So I let them think about it for a few minutes, and then I tell them, so sorry, I was being mean. There isn't really a reason. And I think you have to be very wary of sort of numerology. If you look at enough questions or enough things, the chances that you see two that are the same get larger and larger and larger. I think that's where it comes from at the end of the day. It's actually a technique that a problem that has to be used in statistical analysis. So if you're looking for signatures in data, you have to allow for the fact, allow for how many experiments you've done, how many times you've looked for this thing, to ensure that you're correctly calculating the number of random coincidences you might have got.
Thank you. Just belief, but nothing scientific proof. Thank you.
I don't know, of course, but that's my feeling. Yeah.
Thank you.
Okay, Fabian.
Thank you very much, Tim, for this wonderful presentation. I have basically two questions. One is on the nature of space-time. So first, like the common belief, or what I know is like the origin of space-time has to do with the expansion of the universe itself. So how does the propagation of space-time with the expansion of the universe happen? Is there any explanation for that process within science, or rather within physics? That's the first question.
Well, this is difficult. Space-time and gravity are actually the same thing. That's what general relativity is really telling us. And space-time is influenced by matter. So all three things, space, time, and matter, are intimately linked. And when something like these universes created and a Big Bang happens, it's tempting to think of something occurring in space-time and matter expanding into a pre-existing space-time. That's not the case. In fact, the entire construct, space and time and matter, are all forming simultaneously. Okay, so it's very difficult to, if not impossible, I think, really, for us to have a good intuitive picture of what's going on, because it's just so far removed from our daily experience. The kind of things that people try and do to explain what's happening, you know, if you have it doesn't really work. Okay, so people talking about things like, you know, blowing up a balloon, and if you draw something on a balloon and you blow up the balloon, then you see how the circle or whatever you've drawn on the balloon, how it expands as the balloon expands. And that's supposed to be a sort of 2D analog of space-time expansion with material in being forced apart by the expansion of space-time. And it sort of works, but you know, all these things are rather limited. So this is one of the places where it's very difficult to get intuition, and you actually have to fall back on the mathematical understanding of what's going on.
Thank you very much, Tim. I suspected as much that question. My second question is, right, like I read about certain models that explain the nature of the universe, especially when it comes to string theory and so on. So in these models, they have certain, they describe the universe using certain quantities or dimensions, but like they describe the universe using, you know, a larger number of dimensions than what we are normally aware of. So are these dimensions basically, is there an analog physically, or what sort of what is basically the nature of these dimensions that they speak of in these models?
Yeah, okay. So they would be real dimensions, but in the current universe, if you know, they're just extremely small compared to the dimensions that we experience day to day. Now, apologies again for this. So Can I think of a good one? Okay, so this isn't really what I want, but try and explain the idea. If you were an ant, and your world was a hose pipe, okay, and you were living on the surface of the hose pipe, then, because the hose pipe is small in the round direction, you might only see the direction along the hose pipe. So you might think you're living in a one-dimensional world, where you can walk along the hose pipe, or you can walk backwards back to where you were, but you can't see anything beyond that. And actually, you're in a two-dimensional world because you could go around the hose pipe as well, but that just dimension is just so small that you as an ant don't spot it. And we would be in a similar situation. We'd be in a world we see as having 3 space dimensions and 1 time dimension, but there are other dimensions that are just so tightly curled up that we don't see them. Could we actually spot these in any way? Well, one of the possibilities would be actually to do some of the experiments we could do with CTA. If you use extremely high energy photons or other particles, the size of an object, the wavelength of light, for example, decreases as its energy goes up. So if you could get a high enough energy in your light particles, their wavelength is small enough, they might start to be able to interact with the very, very, very small dimensions that some things like string theories suggest may also be present in the universe. And so you might see the way that light moves change as you go to extremely high energies. So that's actually an experiment we'll try and do. So far, the limits are no, I have to be careful there. I think the limits are around about 10 to the 21 electron volts in terms of the energy of photons, which have already been used to do these investigations, and nothing has been seen at that equivalent size scale as yet. About that number.
Thank you very much, Tim.
A follow-up question from me, Tim, to you. This famous thing about, if you get a strip of paper and, we stick it together, and an ant going round on one surface can only have one surface, whereas if you do a twist, then two.
A Mobius strip.
Yeah, that's what it is. Yeah. So we know that in physical world, the 2 spaces can be merged. I mean, is there any evidence that similar thing could happen in sort of more larger scale?
There is certainly evidence that the geometry associated with aspects of reality is not as simple as we might assume. So actually, I've got a cup of tea here. So I'll see if I can show you one of these things. So if I take my cup of tea and I want to rotate it, okay, so I've now got to make sure I don't spill it. Okay, so I've now rotated that by 360 degrees. Okay, so you'd have thought that should be the same. If you to spin something through 360 degrees, it looks the same, but it clearly isn't. I have to go another 360 degrees before I get back to my starting position. Okay, So that is actually what you see in the behavior of electrons. So topologically, electrons and other particles which have a property called spin of half behave as though they were that cup. So they're like something connected to with a string to the external world. So you have to do a 720-degree rotation before you get them back to where they started from. So certainly, yes, there are geometrical properties of physical objects which are not what you might naively expect. Yeah.
Okay. Thank you very much. Another question from me. So from my understanding of the special theory of relativity, Einstein suggested that when the velocity of a mass gets closer to the light velocity, the mass increases. Right? So now you are talking about these cosmic particles as actually having some mass. How come that they even probably increase this the light without increasing the mass?
Well, whether you call that mass or energy is the question here. So what a more modern formulation of special relativity, people wouldn't talk about the mass varying, they talk about the energy of the object. So when you talk about the mass nowadays, you mean the rest mass, the mass it has when it's sitting still, and the energy of a stationary mass would be mc squared. Yeah. The energy associated with moving mass would be E gamma mc squared, where gamma is the factor which tells you how much the energy increases as the velocity increases. Now, what Einstein originally did was he called mass gamma m, which we just don't do nowadays. So it's a question of semantics rather than anything. So when I talk about a photon having a very, very high energy, it's not associated with a mass. We'd still say the photon has zero mass, it just has a lot of energy. If it's a proton, again, nowadays we talk about the proton having a particular fixed mass. It would correspond to an energy of about 1 GeV in its rest frame, but it might have a much higher energy when okay, and we wouldn't nowadays really associate that with an increase in the mass of the proton. It's just not a helpful concept, really.
Thank you very much. Any other questions from the audience? Shihan.
Yeah. Thank you again. Just another question, just from what you said just now. If the photon, as we know, doesn't have a mass, then theoretically it's possible to have infinite acceleration to a proton. So why doesn't this kind of thing happen? In other words, if you, in any object, if you can reduce the inertial mass, then you should be coming to a situation where you can accelerate it beyond the speed of light, kind of.
No, if you've got zero mass, you have to travel at the speed of light. You can't sit still.
But can't you exceed it?
No, no. The only way you can exceed the speed of light would be to have sort of virtual mass in Einstein's equations and an imaginary mass. Yeah, so you've got an equation E squared equals P squared plus M squared.
Yes.
Powering factors of C, and if you want to get it, when you turn that into velocities, you'll find you'll get a square root in front of a mass. If you want to get the get velocities above C, you've got to have an imaginary mass, and those things, particles of that nature, would be are called tachyons.
Yes, I heard.
There's no evidence for their existence.
All right, yeah.
And they're very problematic. they would tend to do horrible things like spontaneously get faster and faster velocities and violate energy conservation and things like that. So they're pretty difficult beasts to deal with.
Yeah. Okay.
There's
no evidence at all for the.
No. People have actually looked for them,
yeah.
And they've done it by looking for signatures of things that happened before an event. So, for example, if you had a supernova, you could look for something that happens consistently before a supernova. Yeah, there's no evidence for anything like that so far.
Yeah, thanks.
Okay, any more questions? Right, I think it's time to wind down now. Can everybody unmute yourself and probably put on your videos as well, as usual? So, Tim, it was our pleasure to have you. And I think you didn't expect this amount of questions probably today from a non-physics audience. And I hope you enjoyed it. But I can only speak for myself. I really and thoroughly enjoyed this lecture. And one of our colleagues who has been speaking to you earlier, Pavan, said that he would have a follow-up discussion about astronomy. So we are very, very thankful to you for the presentation you did for us today. Thank you very much.
Thank you then. Have a good day, everybody.
Thank you. Thank you.
Bye.
Bye-bye. Bye, everybody.
Bye-bye.
Bye.